Hello AP students, how we all doing today? Sorry, what? Can you say that again? What? What? I can't hear you. All right, well, I'm just, what? Wait, I'm sorry, I can't hear you. I'm just gonna keep going, even though I can't hear you. So this is the problem I had passed out in class on Friday. If you weren't here in class on Friday, there is a picture of this problem available on the notes that were posted. And the problem goes a little bit like this. Suppose a company manufactures two cylindrical tubes where tube A is designed to fit snugly over tube B. The diameter of tube A is manufactured with a mean diameter of 7.84 centimeters and a standard deviation of 0.08 centimeters, and it follows an approximately normal distribution. The diameter of tube B also follows a normal distribution with a mean of 7.46 and a standard deviation of 0.11 centimeters, which is what you could see what I wrote here and there. And I'm erasing those marks now. Okay, so part A asks, what is the probability that a randomly selected tube A has a diameter of 8 centimeters or greater? And you might look at this and try not to overcomplicate this, because we're just looking for, well, here's tube A, here's tube B. We're just looking for the probability that some randomly selected tube A has a diameter greater than 8.0 centimeters. So we can solve this in a few ways. I'm going to take the z-table approach here. I can say, well, if I subtract the mean from each, the mean is going to be 7.84, standard deviation 0.08, and then I do the same thing on this side. Excuse me, that shouldn't be an 8. Should be the probability of 8.0, excuse me, minus 7.84 divided by 0.08. Why did I do all that mess? That's going to give me a value of z there on the left. And then if I actually calculate this z-score, 0.16 divided by 0.08, isn't that nice? That's going to be 2.0 exactly. So I'm essentially looking for what the probability that z is greater than or equal to 2, but of course since this follows a continuous distribution, I can drop that inequality sign. And from this, I'm going to use the table. The table always gives me probabilities less than some value of z, so I'm going to have to use the complement rule. And so this is going to be 1 minus the probability that z is less than 2.0. And if I go to my normal table, and I just luckily happen to have a normal table in my back pocket, the area that corresponds to z equaling 2.0 is going to be 0.9772. So this is going to equal 0.0228, or a 2.28% chance. Is that the only way to solve it using the z-score? No, it's probably going to be a little faster if I use my calculator. If you're going to use your calculator, this is what you need to show me. Number one, you're going to take the bell curve, and okay, here's the mean was 7.84. And I'm looking for the probability that it's 8.0 or greater, so I'm looking for this region. And I'm looking for what's the probability in this case, some value of 8 is greater than 8.0. And I'm going to go in here, normal CDF on my calculator. And if we recall, we put LUMs, lower upper mean standard deviation. I can tell by my drawing the lower is going to be 8, the upper is going to be infinity, so I'll put a bunch of 9s. The mean was 7.84. And the standard deviation, excuse me, I'm running out of room there, was 0.8. And again, I can do this in my calculator, and if I do this on the calculator, normal CDF 8, comma 99999, 7.84, comma 0.08. I also get what I pretty much got before, 0.022750062. So as you can see, what's nice about the normal CDF function is I get even more accuracy than I would get from the table. Awesome. Now, if this were a test, is this good enough? For this particular problem, since it's just asking one question, it's not asking it's not asking for a four-step process, but I may as well just back myself up and say there is a 2.28% chance that a randomly selected tube A, tube A, I know it sounds awkward, but it's all right, is 8 centimeters or greater. I know the question asked for the greater than or equal to, we know we can drop it on a normal distribution, but since that's what the question asked, that's why I'm going to throw in that or greater part. Okay, part B of this question asks, are the diameters of tube A and tube B independent? Explain. Well, what does it mean for them to be independent? It means that one doesn't affect the other. So in this case, we're looking at the manufacturing of these particular tubes. Is the manufacturing of tube 1 or tube A independent from tube B? And if you reread the problem, I'm reading it again, and I think I left out a little detail. Let's assume for now that they were made on different machines. But I would say that we don't know for sure, even if we didn't know they were made on different machines, I would say it is reasonable to assume, since we don't know for sure, we would say it is reasonable to assume that that the diameters manufactured, since we're looking at the diameter, that's our variable, is the diameter. The diameters of tube A and B, tube A and tube B, are manufactured independently. That word did say manufactured, believe it or not. Independently, I'll say since they were probably made in different batches. Most problems should give you a little bit of a more clue, since they were probably both made in separate batches, both made in separate batches. There was a little detail I left out of the problem. I was going to mention that they were made on different machines, and that should definitely, if they were made on different machines, definitely be independent. So there hopefully is some kind of clue in a problem that should tell you whether the two variables are independent. If not, tell me why it should be reasonable to assume that they are independent. And if we're going to take this much work to make a problem, chances they should be independent, the two random variables, because if they were dependent, there's nothing we could do with our current state of knowledge. Okay, part C. This is where we're going to get a little crazy. You ready to get crazy? I was born ready. Okay. In order for the tubes to fit properly, the difference between tube A and tube B cannot be less than 0.15 centimeters. That would make them too tight. And they cannot and they cannot be greater than 0.06 centimeters. That's going to make them too loose. So let's use the four-step process to determine the probability that a randomly selected pair of tubes will fit properly. Okay, so I'd kind of set this up. I have a shop vac at home, those vacuum cleaners that you use in the garage, and usually there's an extension of one piece or the other, and they have to fit properly. If it's too tight, it's not going to work. You won't even be able to squeeze one in, and if it's too loose, it's going to fall off when you're using it. So it needs to fit just correctly. So we're going to use the four-step process, and let's recall what the four-step process is. You knew that already. I knew you knew it. State, plan, do, conclude. So let's start with the stating. State, what do we do for state? We reword the problem. So we are looking for, I would say we are looking for, or we can ask a question, we are looking for the probability, probability that a random pair of tubes now, I would say fit properly, but we've kind of defined what fit properly means. It could either be too tight or too loose, or it should be in that Goldilocks zone, I reckon. So we're looking for the probability that a pair of tubes would be greater than I'm leaving out a detail because we're not looking for the actual probability that the tubes are. We're looking for the probability that I'm going to go back here and I apologize for erasing this, but that's okay. It's a learning experience. It's not the probability that we're looking for a pair of tubes. We're looking for the probability that the difference between a pair of tube, that the difference between a pair of tubes is greater than 0.15 centimeters and less than 0.6 centimeters. So it needs to be in that Goldilocks zone. So that's the state part of the problem. So in the plan department here, let's plan how are we going to do this problem. So I would start out by saying we will let, we'll say D equal A minus B. A was the bigger tube, B was the smaller tube. B is designed to be the smaller one, so that's the one that's going to fit inside of A. We will let D equals A minus B represent the difference between tube A, represent the difference between the difference between the diameters. I know I'm getting a little lax with saying between tube A and tube B, but what does that even mean? I'm not looking for the difference between tube A and tube B, but I'm looking for the difference between the diameters. That's my variable. It's not tube A and tube B, but it's the diameters of tube A and tube B. Let me make sure that sentence makes sense. We will let D equals A minus B represent the difference between the diameters of tube A and tube B. And that was where it said and tube B. Then we want to calculate. What do we want to calculate? We want to calculate the probability that the difference is between 0.51. I'm going to take out that equals sign because we don't really need it. And 0.06. So that's the planning part of the problem. So what are we on here? So we are on the doing part now. State, plan, do. Let's do this. How are we going to do this? Well, since tube A and B are independent, I think it's fair enough right now to say, since A and B are independent, and both follow an approximately normal distribution. These are important, these conditions, by the way, and I'll explain that in a minute. And since both follow an approximately normal distribution, we can use I won't say not we can use, but we can, or we know, how about that? We know that D will also follow a normal distribution, approximately normal distribution. That was a P, believe it or not. You don't believe me, it was. Normal distribution. So whenever something follows a normal distribution, we're going to need to know the mean, and we're going to need to know the standard deviation. So what is the mean of D? Well, we defined the mean of D, mu of D, is going to equal mu of A minus minus B, and the mean of A was 7.84, and the mean of B was 7.46. So the mean is going to be uh, 0.38. And what's the standard deviation of D? I want to remind you, even though we are subtracting the two, what do we do with the variances? We still add the variances together and square root the variances. So this is going to be this. It's going to be the square root of those guys, which is going to be, these numbers were given to us. It was 0.8, 0.08 squared plus 0.11 squared. And if I do that on my calculator, if I'm brave enough, I can do this all in one line on my calculator, which I'm doing because I'm brave. No big deal. Okay, fine, it's a big deal. I got 0.16. So we know now that D follows an approximately normal distribution with the mean of, what was my mean again? 0.8. Sorry, 0.3, it's that number, 0.38, and the standard deviation we said was 1.136. So again, let's remind ourselves, what are we trying to solve? We were trying to solve what's the probability that, let's go back here, I forgot. It's going to, right down here, we're trying to find that probability. It's between 0.15 and 0.6. Or if I draw this out, this is going to have a mean of 0.38, and here's 0.6 over here, and here's 0.15, and we know this has a standard deviation of 0.136. Actually, it's already written above there, and I'm trying to find this beautiful area right in between here. That looks nice. I'm going to go ahead now and just use technology. I could do two z-scores, but I think it's getting a little cumbersome here. So this is going to equal, I'll say normal CDF, and my lower is 0.15, my upper is 0.60, my mean was 0.38, and my standard deviation was 1.36. Oof. Lights at the end of the tunnel. We're almost done. Whoever thought this video would take over 20 minutes? Well, it hasn't hit the 20-minute mark yet, has it? Has it? Has it? Yeah? No? Oh, no. There it is. Ding, 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 ding. Winner. Yay. You've survived. 20 minutes. Did you really listen to me talk the whole time? Good, good. Sorry, I'm working out this problem here. Inverse norm. Oops, not normal. Supposed to say normal CDF. There we go. 0.15, comma 0.6, comma 0.38, comma 0.136. Numbers just roll right off the tongue. 0.9017. Woo! Yeah, we're done, right? Wrong. We're almost done, though. Plan, state, do, we just did. Lastly, we got to conclude. So what color should I use? What? Purple? Okay, purple. All right, conclude. Let's conclude this puppy up because we are almost done. We did all the hard work. So we have calculated that there is a 90.17, right? Was that my number? Yep. 90.1% chance that a randomly selected pair of tubes pair is going to mean both of them of tubes will fit properly. Yeah. That's pretty good. We did it. Was that hard? Yeah, I think it was a little hard. Hopefully you got all these steps. Hopefully it made sense. And feel free to bring in any other questions. And thanks for suffering through all 21 minutes and 59 seconds.